Okay, let's get started. The exam is next week over the weekend. I'm not going to move it unless there's absolutely like tons of people who complain to me. I looked around a bunch and there aren't that many. There's one exam that I could find that was PDEs on the Monday during the exam time. And if we move the exam, it's just going to cause other issues. So it's going to stay put. I apologize. The exam is meant, again, to be done in a day. So you have 4 days to do it. And if you need to take one of those days to study for another exam, that is why I give you 4 days. Okay? So if you still have a huge number of exams, come talk to me or send me an email individually. And then we can talk about moving it or adjusting it accordingly. The other thing about the exam is, again, the last homework that concerns material in the exam is due this Thursday. That will lead us all the way through differentiation and quadrature, and that is the limits of the material. We will start on ODEs, possibly today, but just to remind you, don't worry about it. That is not on the exam. That will be ongoing. So we'll have today, Thursday, and next Tuesday will just be lectures primarily on ODEs. And then the Thursday before the exam, we will go over the midterm review, which is a bunch of questions that are the type of questions to expect on the midterm. And we'll just basically do as many of them as we can the Thursday before the exam is available. So that's the plan. The midterm review, I'm putting together a bunch of questions. It'll be made available when I get that done, because obviously we don't need to worry about it being available for a certain amount of time. So I want to give you as much time to look at that. Definitely suggest doing the midterm review, or at least looking at the problems before the Thursday, because that way you get more out of it. And I guess I'll probably have more to say about the midterm review once I get it done myself. So are there any questions other than that? Yeah. Absolutely. Any other questions? One thing that always does come up on these midterms, because they are open book and now open internet, because books are on the internet. If you do have a question about using material from the internet, please ask me, because in the past someone has found, unfortunately, the answer on the internet, and we can't really have that because that's not really fair. So if you do, the rule of thumb is basically you need to be writing it of your own accord. I try very, very hard to write my own questions, but inevitably, if someone looks hard enough, a lot of problems have been solved that are solvable, so it's always a problem. If you have plagiarized material from the web, you will get a 0. So if you have any question about it, please ask. That is the rule of thumb. Obviously, you can't work together. You copy off someone else. That's also not only considered cheating, but also plagiarism. Plagiarism is just another form of cheating. So be aware of those types of things. Yes? Yeah, that's fine. But by and large, I mean, we can use the stuff that we've used. You can't, if I ask you to write, say, a golden section search, you can't use scipy.optimize golden section search. But if you have a question about that, the best thing is just ask about all that type of stuff. Again, it's hard to know if you find some obscure package that does the entirety of the question for you, it's probably not going to fly. So, but if you do have a question about it, just please ask. Yeah. There will not be one, no. So the last homework for a little while is going to be due this Thursday. And then you'll have the midterm review, which you don't have to turn in. Homework will start again after the exam. Any other questions? Yes?
So partial credit for questions, is it? Can't solve one, and then you should be.
Yes. Partial credit's a thing, for sure. If you don't get all of a particular problem correct, but the code is mostly right, you just had a bug in it, you couldn't find it, We'll give you a partial credit for that, for sure. Any other questions? All right. So hopefully today we're going to finish up quadrature. Kind of where we left off was talking about trapezoidal rule, and trapezoidal rule being a particular case of Newton-Cotes quadrature. So just to remind you, Newton-Cotes has this basically very basic form. We say we have n plus 1 equally spaced points, and we just want to say, I want to take the interpolating polynomial that goes through those evenly spaced points, and I integrate that polynomial. So the polynomial approximation to the function f, and then I use that to approximate the integral of f instead. So very straightforward, where you can use any kind of interpolant you want, the basis you want, and we went forward. First one we looked for it was trapezoidal rule, which is just a case where we have a polynomial that's a linear polynomial. You integrate it, and you get the rule back out. And then we just talked really briefly about the fact that you can kind of combine each of these partitions together so that you don't have to compute a bunch of them extraneously. So the first thing we're actually going to do to get started is just to code this up. So I want to give you a chance to do this first. It's a for loop. And we're going to calculate the cumulative integral. Here I've given you the first one, so I had 0 is just this part here. So you want to calculate the sum. So give that a try, and take the time to just remind yourself of what we're going about this. And we got the trapezoidal rule, and then we're going to do the same thing with Simpson's rule, which is just the quadratic version of the Newton-Cotes quadrature. Okay? So I'll give you a couple minutes for that, and then we'll code some things. Okay? Okay, so there's just 2 lines to add here, and it's going to be a loop. Unfortunately, we can't quite do this in a vectorized form because we need the calculation from the previous integral all the way up to that, the way we're doing the cumulative integral. In principle, you could actually just recompute a bunch of things, but in this case, a for loop is the right thing to do. So we're going to go for I in range. 1 to num partitions. So really, the number of partitions is somehow represented by this n minus 1 in this case. And and num partitions is we're going up to the num partitions, but of course by Python, it's one less than that, which is why we actually don't include that n minus 1 there. And we're counting from 1 because we already did 0 for that part. So we're going to do the same thing we did actually above, where we're going to calculate the ith one. We're going to add to it the I minus 1, and then we're going to calculate each of the terms. So if we look up here, we just need to do delta x times f, which actually was part of our simple version of it. But because it's a trapezoid rule and it's kind of being added together, this actually ends up giving you a more accurate version of this, which is nice. Okay, so, oops, I did that wrong. What did I do? Oh, I got to do each term individually because of the way I did this. I minus 1, I plus 1. I missed that. Oh, does anybody see what I did wrong? Oh, is that? XChat. Okay, there we go. Phew. Bugs are always scary. So you see, we have a partition, and from the eyeball norm, just looking at the top part, you can see that these piecewise linear functions basically are approximating the curve much better than we had before, where it was just the left-hand rule or the midpoint rule or the right-hand rule. And we approximate the integral fairly well in this case. So the other one we'll talk about, and this is kind of where we usually stop in terms of talking about this in calculus. What is Simpson's rule? So Simpson's rule is another Newton-Cotes rule. It's the n equals 2 order polynomials. So we need 3 points, so it's quadratic. So here's the quadratic polynomial written in a particular way so that we're actually on the interval that's taking into account the partition of delta x width. So it looks a little bit more complicated than it would usually be, but basically we have the same type of thing. So we have, in this case, x minus delta x over 2, x minus delta x. So this is going to be a quadratic polynomial, and we can kind of see that we're evaluating it at various points. If we take that polynomial, so that was just the interpolant. We still have to integrate it. If you go through that effort, integrating from xi to xi plus 1, so that's defining the partition, we get this rule back out. So xi plus delta x over 2. So this is just the midpoint between xi and xi plus 1, using 3 points inside that partition, and then the final right-hand side evaluation of this thing. So that's one way to do it. You can see this is going to get kind of progressively more complicated just due to the fact that we're constrained to be on a partition. And oftentimes we're going to write the quadrature rules in terms of xi and xi plus 1, and then you start getting these offsets on the partition. So another way to do this is actually by using method of undetermined coefficients. So very similar to what we did with finite differences. The basic idea is you choose a stencil. So again, here we're choosing 3 points that we're going to evaluate the function f at, and where you need to determine what those weights are, w0, w1, and w2. And we want it to approximate the integral. Seems like kind of an obvious thing. So the way we do this, or one way to do it, is we need to find 3 constraints. So in this case, our method is quadratic. We expect to be able to integrate any quadratic polynomial. So the function f could be a quadratic polynomial. If we're doing the interpolant of a quadratic polynomial and we're integrating that, we should get the exact answer back out. In fact, anything up to a quadratic polynomial, we should get the exact answer back out. Okay? So that gives us 3 constraints easily. So why not choose the easiest things? So here we're integrating, we're saying f is equal to 1. We integrate that. So the interpolant of f is equal to 1 of a quadratic just gives you back 1. And so the integral is delta x of that thing. Okay? If we let f equal to x, again, it's less than a quadratic, we integrate that x, and we get back out delta x squared over 2. So again, the exact answer should be this. And finally, because we can go up to x squared, we plug that in, we take the integral of it, we get delta x cubed over 3. Okay? The fact that we're going from 0 to delta x doesn't really matter. We can always transform it into another interval. So we could go from xi to xi plus 1 as long as delta x is. This is just an easier way to say xi is equal to 0, xi plus 1 is equal to 0 plus delta x. So completely generalized that way. You can also, of course, pick 3 other different functions. The only key thing here is that we kind of want them to be orthogonal to each other or in some sense. So that really means in polynomial language that we need to take a monomial of 1x squared, or something that's a constant, something that looks linear, something that looks quadratic. Just so happens monomials are the easiest things to integrate, so they work great in these cases. So we have 3 different constraints. We want our integration, our quadrature rule, to be exact in these instances. We have 3 unknowns. We have 3 constraints. We can write a system of equations. So think about this. Make sure that this makes sense to you, because this is a little weird. Convince yourself that this is the case, and then actually try to write down the system of equations we're going to have to solve. We know the answer already. It's got to be this thing somehow, but there should be 3 equations here that you can find in these constraints. Okay, so I'll give you a couple of minutes for that. Definitely talk with your neighbor. See, check to make sure that you're getting the same constraints. There are other interesting constraints that always come out of these too. You may see a pattern similar to the one in finite differences, which isn't surprising. This is the inverse of a difference, so things tend to work out this way. Yeah, so I'll give you a couple minutes for that, and then we'll code it up. All right, so let's go through this piece by piece. The first constraint here is we have f is equal to 1. So we've just in the integral, we think that that's equal to delta x, or we want it to be equal to delta x. Now what we're going to do is we're going to go up to this, our weights with all the function evaluations, and then we say, okay, so if I evaluate f at 0, what do I get? F is equal to 1. What if I evaluate f at 0? I get 1 back out. In fact, it doesn't matter where I evaluate f, it's a constant, it's always 1, which means that delta x has got to be equal to w0 plus w1 plus w2. Okay. Similarly, for f of x tilde x, so we think that should be delta x squared over 2. I'll go back up to my original function, and I evaluated it at the zeros. So f of 0, evaluated using x, means it's 0. So w0 is out of the picture. I get delta x over 2, and then I get delta x. So I end up getting w1 delta x over 2 plus w2, w somehow, and this is going to be delta x. Okay? And then the third one is basically the same thing. We're just evaluating at the same piece. So note that the kind of simplicity of these monomials is actually important. If we did make these more complicated, we would just have a more complicated set of equations to solve, and no one likes that. So we got delta x cubed over 3 is going to be equal to w1 of delta x over 2 squared plus w2 delta x squared, just like that. 3 equations, 3 unknowns. Notice these are linear equations. They have squares and things like that, but we don't need to know what delta x is. We need to know what w1 and w2 and w0 are. All right, so if we actually write this down in its full form, we're going to concentrate on these 2 equations because they don't have w0 in them. Solve for one, plug it into the other, and then finally get w0, which will be basically the leftovers. So we can write down this linear system here. And this also kind of should look like things from like interpolation and things like that. Oh, yeah, you have a question? Yeah.
How did you get 6 in the denominator?
That might be a typo. Probably. Did I fix the typo? I fixed it here.
Okay.
Totally a typo. Thanks for catching that. Yeah, why would I get a... Anyway, I probably cubed it instead of like thinking about it. Anyway, so we can solve this system of equations, doing various means. For instance, like in this case, I actually just normalized by delta x. So just putting all the delta x's on the right side tends to normalize things. We kind of expect that since we only really get delta x's, because delta x is still that width of that polynomial, or the partition. So having only a single delta x is important. Also, via dimensional analysis, we need to have a length in our integral in order to get areas back out, because we also have the height of that integral. So we also, again, kind of expect this to simplify quite a bit, regardless of the powers in here. We solve this equation. Here we have an upper triangular matrix, so we know we can do backward substitution, which we will talk about in a few weeks more, and we can actually solve these things. Okay? So note that this is actually very algorithmic in principle. You could go cubic, quadratic, quartic, and higher and higher and higher if you'd like. You just have to solve a growing system of equations, which we know we can do. Okay? So let's actually implement this. This one's slightly more tedious due to the growing size of the stencil. So I'm just going to do this for us. And it looks basically like it did before. And this, again, is the cumulative integral. And I've helpfully not deleted the one above it. So we're going to copy and paste that, because this is, again, going to be helpful for us. And we just have to change the indices that we're actually evaluating this thing at. So here we have fx hat 0 and fx hat 1. So that's because W2 and W0 have the exact same value. So we're just adding them in there. So I wanted to do fx hat and I plus 2, I minus 2. That's what I want to do, I think. How am I actually centering this? Oh, it's I plus 1. Yeah. So I could actually probably simplify this down actually a little bit, but. And then we have fx hat I, oh, sorry, I was getting ahead of myself. We're going to do this a little bit more complicated in a little bit. The partition's still defined as x hat I to x hat I plus 1, and I'm just moving around where that's being evaluated in this case. So hopefully I got that right. Okay, there we go. You know, we really couldn't see it when we were using trapezoidal rule, but now because there's a quadratic in here, it's going to be, at least by visual inspection, even closer to the curve. And we're actually going to eventually show that this is even a better algorithm to do integration if you don't mind using it, because it is a little bit more complicated. All right. Any questions about that? Yeah. The coefficients will be very similar, but you're right, because you'd have to change the delta x. That's part of the mapping part. That does bring up a good thing. On the homework, when I ask you to map a quadrature rule from 0 to 1 to 0 to delta x, be very careful about how you do that. It is just a substitution of variables, just like you usually do when doing integration. But instead of concentrating on the integrand and making it easier to integrate, you're concentrating on the bounds and making the bounds match what you want. Okay, so it's a little bit different than what you always would do in, say, calculus. In this case, we want to change the bounds, and the integrand itself will come along for the ride. Okay? So a lot of times when we write down these quadrature rules, they're going to be on some sort of interval that we just arbitrarily choose, either because it's easier to write it down or because it's convenient. And then what we do is we transform it. So we'll go through a little bit more of an explicit version of that as well in a little bit. Are there any other questions? All right. Okay, so we've talked about a couple different quadrature rules, kind of the things that you probably should have seen in calculus at some point. So before we go any further, let's talk a little bit about error analysis, because before we start talking about maybe why you don't want to use Simpson's rule or trapezoidal rule, there are better rules out there, we need to talk about why they're better. Okay? So error analysis, I think I said this last time, but we have some quadrature rule. In general, they look like this. Some weight times f evaluated on the partition a bunch of times. Okay? So this can be all sorts of things, and note that this is just one partition. This is the definition for one partition, and you have a bunch of weights inside of that partition. So the xi's in this case are not representing the partition, other than they could be x0 and xn-1 could be the edges of the partition, but that doesn't even have to be true. But we have pairs of wi and xi. Okay. So given that, we're going to define the error just as the true solution is going to be equal to our approximation plus some error. Okay, it's the leftovers. The other way you can think about this is if I take IF, subtract IN, so true solution minus our approximation, we should get error back out. Okay, so the same exact type of description. In this particular case, oftentimes we're talking about polynomials again, because we can integrate polynomials. And so what we're going to do is just basically look at this and say, I can, in various contexts, know that the approximation to f, the interpolant, and then therefore the integration, I can identify what this error term looks like. It's going to be the remainder integrated, just like for finite differences. So let's look at that. Okay, so if we use Lagrange's theorem, which is one of the basic theorems we have, we know that that remainder term in terms of the interpolation by itself, so approximating the function f, looks like this. We have our roots where the interpolation points were, and then we have some term over here which is dependent on n+1 derivative of f, evaluated at our favorite constant c, which is something or whatever. So in general, again, we kind of think that this is constant, and we're more interested in how this is behaving. But in reality, for integration, of course, we actually have to integrate this, just like we had to take the derivative before. So the integral, the quadrature rule is here somewhere. So we're integrating some polynomial. And then we do the same thing to the remainder. Okay? So, and that gives us our error. So the error is going to be equal to the sum over all partitions. So now we're actually adding up over partitions of xi to xi plus 1. And that gives us this. You can actually talk about the error for one partition. But you have to be careful. You just have to make sure that you understand which kind of error you're talking about. Because if you're talking about one partition, that's going to be usually an order of magnitude difference than for all partitions, if capital N is big. All right, so you're adding either a bunch of errors together that could decrease what you look like your error might be, or if you're just talking about one partition, you're going to get another error constant back out. So let's just do a couple examples, because it's usually the easiest thing to do. For trapezoidal error, we know the remainder term is going to look quadratic. So we have x minus xi and xi minus xi plus 1, because those are the 2 points that we're interpolating at. It's the edges of the partition. And we have the second derivative of f evaluated at some c divided by 2. Okay? So if we integrate this, we know how to integrate a quadratic. This just sits here, doesn't do a thing, because we've already evaluated f. That's important. Otherwise, we'd have to know the integral of f to get the error back out. So we get something that looks like delta x cubed over 12. Okay? So now that's the error for one partition, is delta x cubed. We'll actually sum up all of those in the partition. We see that, well, maybe we have a c that's changing from partition to partition because that c was actually defined on one partition. The interpolant only lives on one of the partitions. So that's a complication, but by and large, we can usually map that and figure out what's going on. Well, okay, so that's something. But if we actually rewrite this a little bit, we can actually see something a little bit more interesting, and that's that we get b minus a, which is the length of the total interval we're integrating over, times delta x squared, times the average of f double prime. So really, it's trying to take some way to kind of get control over this. So basically, we're trying to find a c that works for all the partitions, or taking the c's, evaluating the second derivative, and averaging them. That's all that term is doing. Okay? But the big part here is that when we look at the error written this way, we end up actually seeing that we get delta x squared back out. So where that delta x squared is coming from is the fact that when we're evaluating this thing, we're actually getting another delta x, 1 over delta x out of this, partially from this piece here, which is why we see the delta x squared. So it's basically, we're getting another factor of delta x because we have to add up over the entirety of the bounds, the interval. Okay? And this is very common. This is basically always what happens when you're comparing the error over a partition versus the error over the entire integral you're trying to take. You get that reduction of a factor. So we would expect trapezoidal rule to be second order accurate because of that 2 on that delta x. The error asymptotically is going to behave as delta x squared. Okay? So as delta x gets smaller, you're going to see a quadratic decrease in the error. That's what you would expect. Oops, oh no. Simpson's rule. So we can do the same thing for Simpson's rule. It is going to be a cubic that we'll have to deal with. Here's the remainder term in this case. Then we're taking this. We find the integral by, well, if we integrate this, we get this piece back out. So yeah, I've actually done a lot of the math for you because it does get a little hairy in this. But an interesting thing in this case, we actually do get delta x to the 4th out. So we went from a linear interpolant to a quadratic interpolant, incrementing by 1. And we went from delta x squared to delta x to the 4th power. This is a happy coincidence. Unfortunately, this does not happen again. If you went to a cubic, you do not get, you get delta x to the fifth. So just how it happens that Simpson's rule is really nice and you end up getting delta x to the fourth. And this is because terms are canceling. So error terms, if you want to think about it in a Taylor series sense, you can do this, all this analysis with Taylor series as well. You actually find out that by your luck, you end up seeing something that's canceling. Okay. Now, this doesn't actually work if delta x is not uniform, so be aware of that. A lot of this stuff is actually predicated on having the partitions actually being equal, or even the points inside of them being equal as well. So if you start moving things around, that can do you in, so to speak. So that's Simpson's rule. But let's look at the practical side of things a little bit here. So here are three different methods and the exact solution to the integral of sine pi x from 0 to 1. We can integrate that. It's always good to check something you know. We get, something 2 over pi, approximately 0.63. Okay? We're just doing one partition for this and just comparing. Midpoint gives you 1. Maybe that's good enough for your approximation. It's a little disconcerting. Trapezoid gives you 0. That's not good, probably. Although we have cleanly bounded 0.63. I don't know. This is a little bit of a particular case of this because, of course, if we're going to evaluate on the edges of this thing, we're going to find out that we're actually integrating over an entire period. In trapezoidal rule, it's not going to get anything in the middle, and hence why it's going to end up being 0 in this case. Obviously, if you add more partitions, you would start to get a better answer, which is what we'd expect anyways. In terms of Simpson's rule, we get 2 over 3. Well, I mean, as good of approximation as 3 is to pi, we're getting something closer. So it actually is getting a better answer right away. Even with one partition, we see that. Okay? So this is something you can always do. If you are curious about any of these types of methods, integrating something you know and then integrating them over one partition can be illustrative, although with the caveat that you may see kind of weird stuff happens, where midpoint is acting better than trapezoid in this particular case. So you can do that type of analysis, but you can do our error analysis as well. So the same type of thing that we did for finite differences, we can do the exact same thing for integration and quadrature. So here's a bunch of code. It's basically doing all the methods we've implemented so far. So here's midpoint, here's trapezoid, here's Simpson's rule. I'm looping over different numbers of partitions. So we're really comparing the number of partitions as we go, and we're going to see how the errors decrease relative to each other based on that. And we're computing the absolute error in this case, since we know it. And it's actually the exact same problem here, except we're using multiple partitions. And then we're going to use our order C function we saw before. So we're just computing a C to line up things with and plotting a couple lines. So we run this. We get the following. So the blue line is going to be second order. Okay? We don't have first order in this case. We have second order. The green line's fourth order. Haven't seen something that high yet, but we think that Simpson's rule is going to be fourth order. And sure enough, if we actually plot the errors of Simpson's rule, it follows that fourth order. In fact, there's even a bigger constant offset here, which we kind of expected since we just saw that using one partition, Simpson's rule was actually the most accurate of all of them. These other two, they're just kind of going parallel to each other in decreasing at fourth order. Or excuse me, second order, excuse me. Okay, so I haven't drawn another blue line. I could actually do that as well, but you can see that midpoint is slightly more accurate than trapezoidal rule is in this case, and that kind of holds out as to what we just saw as well, just using one partition. So you could claim from this just experimentally that whatever our analysis was, we didn't do midpoint in this case, but our analysis seems to hold up that these are delta x squared or delta x to the fourth in terms of asymptotic error convergence. Any questions about that? All right. There's one other kind of thing that I think is important to think about. So if you're integrating along and you're using trapezoidal rule, one nice thing about trapezoid rule, because it can be nested like we saw, it has a compounding effect. If you decide my integration is just horrible and I don't want more accuracy, you can actually increase the number of points or the number of partitions you're going to use and not have to recompute everything. Okay, so you've computed your integral and you say that was garbage, I need to double the number of partitions I'm using. You can reuse what you've already done because of this nesting property. So that's just making the argument here. So if you say I want to integrate from x0 to x2 using one partition, I get one answer back out. If I instead kind of make this broadly and I use my kind of little fact that I can combine all these things, if I rewrite this in a clever way, I can see, and the reason why I went from x0 to x2, so this is one delta x. If I actually make my delta x half that, I'll get x1 in there. I can rewrite all of this to say that I actually can just evaluate the extra set of points in between all my original points. So I'm having the size of my partitions, but I don't have to do any extra work. Just add those extra points, and I get an increase in my accuracy. Okay? So that's just a nice thing about trapezoid rule. Oftentimes, this doesn't work, unfortunately. For instance, Simpson's rule, this doesn't work because each of the points might actually have different weightings. You could maybe save them and use this, but it's a much more complicated thing in that case. So the fact that trapezoid rule is easy, it has a symmetry to it, is why we can do this easily. Oh, I got ahead of myself. Basically the same thing. You find that the integral where you're using twice the size, so 2 times x, delta x, that's the size of the partitions. Half of that plus the new set of points, so that's why we're f1, f3, whatever, is the same integral, but just doubling the number of partitions. Okay. Let's take a little bit of a side, because we're going to need affine transforms. So an affine transform is really just any transform that's using translation and scaling to do the transformation. Okay? So these are basically the most basic way to move things from one point to another. So vectors and all that type of stuff. Use this all the time in graphics, which is why we can do this very, very quickly oftentimes. In our case, what we're going to do is take intervals and map them to other intervals. We've done this before when we're talking about interpolants. And we wanted to say, I want to be on from 0 to 1 in that case. Here we're going to go from -1 to 1. And that actually is, again, because of interpolation is kind of sitting in the background here. We want to have interpolants that are generally mapped to -1 to 1, take integrals of them, define quadrature rules on that thing rather than the generic xi to xi plus 1, just so it's easier to derive and to also write them down. But we do still want to do this in a practical standpoint. So we want to have the mapping from C, -1 to 1, to A to B. Right, that would be my generic interval. Here's the affine transform. So if I'm going from C to x, we have scaling. Right? So b minus a over 2. It's going to map -1 to 1. It's going to be the size correction. And here we have the translation. So I want to correct the size, and then I move it left to right, however much I need. Because I need to have 0 at the middle. That's kind of the key here. Hence, a plus b is over 2. Now I can invert this too. We get something similar. Okay? So both of these things can be useful, mapping back and forth. In general, we're going to be mapping only one direction for this type of stuff. So here's an example of this. This is the original function I want to, or excuse me, the integral I want to originally do. If I just do this transformation, this is a coordinate transformation, change of variables. I want to go from x to being in terms of c. So I can't really do anything with f. I just plug in what this function up here is. Right? I get some points out here. And note that in general, this would be more complicated probably. But in terms of our quadrature rule, what I really want to do is actually get back the x point that corresponds to a particular c. All right, so this isn't actually that bad. We just get a number back out. But we do have to take into account the fact that we're doing a coordinate transformation. Right? So we get this geometric piece to it. we know how to take derivatives. So take the derivative of this thing. We get back out the scaling, which shouldn't be too surprising. Translation doesn't matter if you transform an integral left to right, as long as the actual integral bounds stay the same, doesn't matter. So that's why we get the scaling piece to it outside of there. And then we just have the new integral from -1 to 1 in terms of actually these Cassis. So we're actually going to be integrating over this. Okay? So in terms of our quadrature rules themselves, we always know we're going to sum over some number of points inside of the partition itself. We have WIs, we have Cassis, so we're going to be defining all of our new quadrature rules in terms of these two numbers. We have this mapping back to x, okay, because we still need to do that. We still need to evaluate f, because f is living in x's space, not Cassis space. And then we have to evaluate this extra term there. Okay, so that's just taking into account this piece. So this is the generic version of all this, just doing the coordinate transformation. This is the more specific to a particular partition when we're doing it. So usually this dx d Cassis clearly is going to be a particular aspect to it. So we actually know in this case exactly what that means. But in general, you could do other transformations possibly that you might want to do. So I encourage you to go back because we actually use this a lot. Basically, we just write down this transformation because we have all the rest of the quadrature rules in terms of these weightings and these points inside the interval -1 to 1. And then we need to transform it back to the correct space to be used. OK. So new things to learn. Hopefully, Simpson's rule, midpoint rule, left-right, trapezoidal rule are things you've seen before in calculus. You may not remember it, but they were there. When we're doing numerical stuff, where we're not talking about limits and things, in the limit, as delta x goes to 0, of course, all these things should give you back the same answer, but we're not, they can't do that on a practical standpoint. So now we're going to talk about more clever ways to do these quadratures, in which we might get better accuracy back out. Okay? So it's a fantastic question to ask. Is there an optimal quadrature method? There is, depending on what question you're asking. So it depends on f. And there's some actually interesting, very deep theory to representation theory behind this. So if you're interested in that, come ask me. I will point you in the right direction. But that's basically the goal. So you note that before, when we were talking about Newton cotes, we were saying the x points that we're evaluating at had to be uniform. We're going to remove that. We're going to allow both the weights and the x's to be movable. So we get another set of degrees of freedom to work with. And we can actually get out some more quadrature rules out of that. So the first one is probably one of the more, the best known quadrature rules in the numerical context. That's Gaussian, generalized Gaussian quadrature. There's a lot of quadrature rules that come out of this. The basic idea is that we have a set of polynomials. So now the basis of those polynomials is important. But we have up to some degree of polynomials. And we want the inner product of those polynomials, g, with the monomials, x to the power I, times some weighting function to be equal to 0. So I call this the inner product, or the dot product, in the sense that this is the continuous version of this business down here. Right? We know if we take the inner product of x and y, if they're two vectors, if this is equal to 0, those two vectors are orthogonal to each other. Right? Same thing goes here, except that I have a weighting function. But this is the same statement. I have to talk about -1 to 1. That's the particular interval we're interested in. But I want my function g, whatever those polynomials are, I want them to be orthogonal to xi for xi less than n, capital N. So that's important. If I was the same power as g, then there would be it would be something. It couldn't be 0 because they're not orthogonal. There are going to be some multiples of each other. But whatever g needs to be, I want these two things to be orthogonal to each other. Okay? And the weighting function is going to determine, basically make sure that I can do this in a reasonable way. We've seen something like this. The Chebyshev polynomials, we've seen the weighting function for those. And that's actually where this is getting at. They're going to be orthogonal in a very similar type of way. Okay? So keep this in mind. We actually have some set of orthogonal polynomials that are orthogonal to everything lower degree than it at this point. Okay? The reason why we want to do this is that if we add another polynomial, a degree polynomial, a higher degree polynomial, we want to somehow be able to approximate more or a more complicated function. And we don't want to add more effort to it. Okay? So by being orthogonal to all the powers less than the one that I'm now at means that I'm actually gaining more information. Right? I'm actually going off in a new direction. There's an infinite number of directions. This could be, capital N can be arbitrarily large. But I want to have something that's going to be orthogonal to all the previous ones that I might want to do. Because, of course, I can always keep on going down in my order of the polynomial. OK, so given the above G, so we're just going to say some G exists, some family of polynomials exists, then there will exist a Wi such that this is true. So we have some polynomial J, Pj. And if I say, well, OK, so this W, if I evaluated certain pieces of it, I can actually approximate that using Wi Pj. And this is starting to look like a quadrature rule. That weight's going to be evaluated at various pieces. But we still have the same kind of request of this thing, that we want to have a polynomial basis function that's going to be orthogonal to all the pieces, all the degree polynomials less than that. Okay? So practically speaking, we've just said a bunch of things. Actually, this is kind of important. Keep in mind 2 times n minus 1. Okay? So this fact that we're requiring orthogonality in this particular way leads to this 2 times n minus 1, which is going to lead us in amazing places, to amazing places. And this is why. So even though we're going to use a polynomial of degree capital N, we're actually going to be able to integrate exactly polynomials up to degree 2 times n minus 1. Okay? So if you remember the uniform case, when we were doing that, we found that we could basically integrate, we could expect to integrate exactly polynomials that were equal to the degree of polynomial that interpolant. That's what we were guaranteed. In this case, because of this extra condition, we can get up to 2 times n minus 1. So almost twice as high degree of polynomial. Exactly. Yeah. All right. So this is the general version of like Gaussian quadrature. Here are some particular cases of this, because basically we've just kind of waved our hands and said that a weight function exists and that polynomial basis exists such that this is true. Well, Gauss-Legendre integration in quadrature uses the Legendre polynomials, and the weighting is luckily just 1. And if we take this, and basically we just actually require that these are orthogonal, we can find out that the polynomial integration weights here look like this. So 2 divided by 1 minus xi squared times the derivative of the interpolating polynomial, xi, and that's squared. Okay? So again, this is coming from this over here. So we're integrating pj times w. So in this case, w is just 1. And then we want to identify the wi's based on that. So that's just solving that system of equations, basically. For that, we get that weighting. The other key here is that the xi's are going to be the ith root of these polynomials. Okay, so that does kind of restrict this. Oh, I also want to say this is not the Lagrange basis. Lagrange basis is not being used. Lagrange basis can be arbitrary. In fact, of course, they could be these, but this is actually specifically the Legendre polynomials. Okay, so we can just write down these things. We showed the general rule, but that's still a little ways from actually being practical. Here's a table of values. So if I have capital N equal 1, xi is going to be 0. So remember, we're still integrating from -1 to 1. So that's our partition mapping. we're evaluating at the middle of the interval, and the weight is 2. Okay. So that's the first rule. The second rule, we're starting to see how this is a little bit different. We have plus or minus the square root of 1 over 3, so 1/3, and the weight is 1 for that one. So we have 2 points. We have n is equal to 2, we have to have 2 points. For n equals 3, we have 3 points plus or minus square root of 3 over 5 and 0. And then we have weights for each of those. And then it gets progressively more complicated as we go. Oh, it's still on. So you can kind of see, I don't think this is going to scroll. There's a few more there that's in the notes that are actually down below. And it gets pretty crazy. You know, you have 322 plus 13 times square root of 70, divide 900. Obviously, that's the number. Why would you think anything otherwise? And the locations of these things are crazy as well. So this is really coming out of just the constraint that we want to have we have a polynomial basis. The polynomial basis itself is also orthogonal to itself, because you need that, otherwise you could break this. Once we have that, and the appropriate weighting function, these things kind of fall out. Okay? So these points aren't going to be uniformly located. We're allowing those to move, and then we get the corresponding weights. Okay, so let's just look at 2-point Gauss-Legendre. So that's, again, n equals 2. We have the 2 weights, and let's actually see if we can figure out how to solve for these things. Okay, so we don't know where x0 and x1 are. We also don't know where w0 and w1 are. Okay, we know the answer. It's plus or minus square root of 1 over 3. And 1. Okay, so those are the things we need to get out. But how do we do this? We do it the exact same way we did it before. We take the monomials up to the point where we think we can go. So this is where that 2 times n minus 1 comes in. We have the monomial f is equal to 1. From -1 to 1, that's equal to 2. It's a little bit different than before. And then we have, well, if you take our quadrature rule, you evaluate it using f is equal to 1. We know that that should be the sum of the weights need to be equal to 2. So that's our first equation. Second equation, similarly, is from before. We get this business here, w0, x0 plus w1 times x1. Again, we have 4 unknowns now. Okay, so that's why we can't just put x0 and x1 in there. Similarly, we get x squared, and then we also have an equation for x cubed. So this is why it's really important that we have 2 times n minus 1, because if we're going to actually find 4 unknowns, we need 4 equations, which means I need to go all the way up to x cubed. So for n equals 2, 2 times 2 is 4, minus 1 means I can go to x cubed. And I can expect that this is going to integrate exactly. That's explicitly how I'm constructing these things, as I want that to be true. Actually, there's a proof as to why you can actually be guaranteed that this should be the case, that you can do it. Okay, so I kind of go on to my merry way, and I get a system of equations here. We get 0, 2/3, things like that. And this is actually why we choose -1 to 1, because there's various cancellations that happen. And if I do my algebra, I find out that the x0 and x1 are plus or minus square root of 1 over 3. And w0 and w1 have to be equal to 2. In fact, I kind of knew that a little bit. They have to sum to 2 here. So whatever they're going to be had to be something simple. Okay. So this is how we actually figure out what these things are. Now, again, you could actually construct a system of equations, but note that these systems of equations are a little bit more complicated. This isn't a linear system anymore. I have unknowns multiplying each other. In fact, not only that, I have unknowns that have powers. So this is no longer a system of linear equations. It's now a system of nonlinear equations, of which they get more and more complicated to solve. Okay, so much more complicated to do. All right, so why not code this up? Okay, so I want to take a little bit of time here. I will code it up. We'll probably finish. How much farther do we have to go? Oh, not too much. I want to give you a couple of minutes just to think about what we just did, because I think if I just code it up for you, you'll probably ignore what we just did. And it'll be lost when you actually get asked about it, maybe on an exam. So take a little bit of time. You don't need to code it up, but look at least how we did that. Think about how the mapping is going to apply, because we do have to implement that. We just found the quadrature rule from -1 to 1. We want to do it over some arbitrary interval. And we need to fill in the bits and pieces of that. And then we're just going to write a cumulative integral again. But, all right, so I'll give you a couple minutes for that, and then we'll finish up our discussion of quadrature today. And we'll scroll up for you if you want to see that. All right, so let's code this up. So we have multiple pieces here. The first piece we're going to do is the mapping. And this actually, you're going to be able to reuse this mapping after we code it up. Multiple times, feel free to copy the code, obviously. Make sure you understand it. Don't just copy it and not enjoy its wonderful implementation details. The way I usually do this, just because it kind of works in my head, is to just write a generic function that just represents the transformation, because we have to use it inside the f's. So I call that zmap, and actually let's just write this into a function. A little bit easier to see. So it's going to take in a, b, and the thing it has to be evaluated, which is c, right? We're mapping back to x. So this looks like b minus a divided by 2 times c plus a plus b divided by 2. Right? That was just the function we defined earlier as the affine transform. Okay. For this particular case, we know the 2 points that we have to do. Those are defined inside this -1 to 1, so that's the Cassis. So we can actually, I'll do it this way. The notes has a different way. Feel free to use whatever you want. So we know that these things are going to be plus or minus the square root of 1/3. Of course, you could, well, we could do that. Do 1.0 divided by this, because of course that's the same thing. And we're going to copy and paste this, because we just need 2 of them, like so. The one advantage of doing it like I'm doing it now is that you can kind of do this for generically. All you have to do is define the weights and the corresponding points, and you're done. And you have a generic code that can do any quadrature rule. So the W's, we'll call it W, we know are 1. All right, so W's are actually fairly trivial in this case, but of course we know that that's not always the case. All right, so I hat. So we're actually going to do the integral. So we have the first, we have it defined here. We of course have to start this thing. So the first point is going to be f at our mapping evaluated at the first partition. Okay, so A and B are the partition edges. So that's going to be x hat 0 and x hat 1 for the first one. And then I have, in this case, the first point, which is C0. And then I multiply by W0. Okay, that's the mapping and the weight. And then, of course, I can do plus, basically the same thing. So these things stay the same because I still have the same partition from A to B. But now I evaluate at C1 and W1. Okay. So you can start to see why this can be a for loop. You can generically have as many of these weights and points as you want, and you can generically implement all of this. Okay. So that was the first one. We're going to do the same thing we did before. We have the commutative integral business here. And then, let's see, let's just actually do an inner loop here. Hopefully I do not screw it up. Okay, so this is going to be the summation, the generic quadrature summation. It's going to go from the length of whatever C is, because I'm going to assume that I have all the points there. So I have this. So I'm going to add to I hat each of the evaluations of the points, which is basically this piece here. All right, except now I'm going to go from I to I plus 1. And C and the W stay the same, except that now I want to have them do the J's. I have an extra parenthesis. Hopefully I did that right. Oh, I need to multiply it by delta x. Okay. So this delta x over 2 business is coming from the fact that I've transformed the integral. So that's the actual Jacobian, if you will, from the integral transformation. So if I didn't screw this up, kind of looks like I did. What did I do? Oh, I didn't multiply by. This was supposed to be over here. There we go. My first one was too much, which of course made everything else too much by the same amount. But here we go. We have our, actually this is generic code at this point. Any time we have a set of points and a set of weights, we can define this. In fact, you can use this for Newton-Cotes if you'd like. And we can do this, and we see that it does a very good job at approximating the integral. So there's other quadrature families. Basically, any set of polynomial bases that has some orthogonality property will be plenty good to use. Crenshaw-Curtis, Chebyshev polynomials, very, very good for various reasons. The weighting is exactly what we saw in the last homework. It's 1 over square root of 1 minus x squared, which makes these things orthogonal to each other. And we know that the roots of the polynomial, exactly where they're going to be. They're going to be the Chebyshev nodes. And we can derive the weights actually fairly easily. So Crenshaw-Curtis actually is a fairly straightforward set of quadrature rules. Gauss-Hermite, just to give you another example, has these weights. You can derive this. This is not trivial. But they're the Hermite polynomials. And you can kind of think like, well, if you have some sort of like physics problem where the Hermite polynomials are the basis of the solution, or maybe you have some other complicated system, but you know that that the solution is fundamentally represented by, say, radial basis functions or something like that, you have quadrature families that might be useful. So that's where all of these things actually come out and can be useful that way. Same type of thing we had before. We can compare all these things. Here's just a different example with the exponential function. We have midpoint, says it's 2. Trapezoid says it's 3. In between the two, so now they've flipped roles. Simpson's rule actually gives you a very good approximation to the exponential function. And Gauss-Legendre, just as an example, 2 gives you slightly better, arguably, just on the other side of it. Okay. Now, to finish off, because we can, of course, do this just to do all of the errors all together, we get this complicated plot. So we have trapezoidal rule, which is second order. And actually, I guess I didn't do midpoint on there. Trapezoid and midpoint, we know, are both second order. Gauss-Legendre 2-point and Gauss-Legendre 3-point are actually, actually Simpson's and Gauss-Legendre 2-point are on top of each other. That's fourth order, right? Gauss-Legendre 3-point is actually going to be fifth order. Okay? So this is all coming from the fact we can actually integrate exactly polynomials 2 times n minus 1, which means we're going further on in the error analysis. And then, not to be outdone, Gauss-Legendre 4-point is down here. It is seventh order accurate. And actually, it tails off here because we've reached machine precision. Okay? So be aware of these types of things. Like, this is so good that it bottoms out. So if you see something and you're like, why isn't this working? It's like, well, look at this side. This says 10 to the negative 16th, negative 10 to the negative 15th. That's why. It's because you can't do any better. You've done it all, succeeded. And I'll stop here with the one note that, of course, SciPy can do this. So as usual, someone's actually sat down and done all this. So if we, oops, that's not what I want to do. We actually look at the scipy.integrate package. There's all sorts of quadrature rules and quadrature rules for double integrals, triple integrals, arbitrarily n-dimensional integrals, because this stuff gets more complicated in those cases. There's all sorts of things here, including things for Newton cotes, Gaussian quadrature, various other types of quadrature, including Simpson's rule. So if you're on your homework or your midterm or something like that, you want to check the answer that this gives you, but you're going to implement it yourself, very key, feel free to check it. That's fine, just to see what's going on. There's other things here about ODE solvers, which is an integration as well. We'll talk about that later. But there's lots of things here. So in the future, if you ever want to use this stuff, you obviously use this, because this is going to be faster and you use code. Okay? So I'll see you Thursday. Office hours are tomorrow for me. Office hours for the TAs Thursday, Friday. And I will see you a little bit later. I think so. It's just